Welcome to the first of 4 videos which will go through some common mistakes that people make in algebraic manipulation and working with numbers. I've called it a baker's dozen because there are 13 separate topics covered in the course of these 4 videos. This first video covers what can loosely be called reading the recipe correctly. That is, can you understand the mathematics that's being asked of you when it's presented in the form of a question? And there are 3 typical things that can cause trouble under this heading. Making sure that you use powers, indexes correctly, how you deal with 0 powers, and also what happens if you attempt to divide by 0. Let's look at the first one concerning powers. A mistake I see fairly commonly when people are using algebra is this one. Minus a squared does not actually turn out to be minus a multiplied by itself. Now, to see that, let's look at a situation that's similar using some simple numbers. Here we have minus 3 in brackets and we're squaring it. Now, it's pretty clear that what we're being asked to do here is square the item that's right next to the power of 2. The brackets are indicating that it's the number minus 3. So in that case we take minus 3, multiply it by itself. 2 minuses multiplied together make a plus, so we end up with positive 9. Now compare that to the statement you see here, minus 3 squared. It is tempting to think that the minus is attached to the 3, and therefore we are still squaring the number minus 3. But the correct way to read this is to note that it's only the 3 that's right next to the power of 2, and therefore that's the only part that gets squared. So dealing with that, we have a minus sign out the front of 3 multiplied by 3, which will of course produce negative 9. Now, what's important in correcting any mathematical error is having some kind of strategy using your other knowledge of mathematics to get around a potential problem when you run into it. Now, in this case, what I think would help understand how to apply the power correctly to a negative number is to think of minus 3 as not just negative 3, a point on the number line, but think of it as a product, minus 1 multiplied by positive 3, because we know that the second item there, minus 1 times 3, is going to produce the number negative 3. So in this case, if you replace the minus 3 with minus 1 times 3, then it's not so easy to make the mistake of squaring the minus 1, because now it looks like the minus 1 is separate from the 3 squared, and that's the right way to interpret it. So now it's pretty clear that it's only the 3 that's getting squared, and we'll get the correct answer. So what we're doing here is using some other knowledge we have about the way numerical manipulation works to help us overcome a potential problem we might be having interpreting some mathematical notation. Because of course minus 3 and minus 1 multiplied by 3 are mathematically the same thing. So they should obey the appropriate rules. Here's a little exercise, 4 little questions. What you might like to do at this point is pause the video, have a bit of a think about which one of those 4 statements is correct. It might be all of them, it might be none of them. Have a bit of a think and then restart the video to see whether you're right. Here's a second set of problems that are similar to the previous set. Note this time that we're raising all of these numbers to the power of 3. So feel free to pause the video and have a think about those ones as well. And here are the correct answers. Item number 2 out of our baker's dozen is what happens when you have a power of 0. Quite often I see people interpreting any number, a raised to the power 0, as equaling 0. Now this isn't true, but it's a natural mistake to make. When we first learn about powers, we learn about whole number powers like 2 squaring, or 3 raising to the power 3, or cubing. Whole number powers are pretty straightforward, but when we start dealing with powers of 1, 0, negative powers, fractional powers, we have to tread a little more carefully because their interpretation is a bit more sophisticated. For this one, a good strategy is to think about index laws that are more familiar to us. So you might be familiar with the index law that says a raised to the power of m divided by the same base a raised to another power n is simply the base a raised to the power of m minus n, the difference between the numerator and denominator powers. Now even if you aren't particularly familiar with that formula, or that shortcut if you like, a good idea is to see what's actually going on underneath the shortcut. So here we have a simple example, 6 raised to the power 5 divided by 6 raised to the power 2. Now clearly what that means is I've got 5 6's on the top line of the fraction multiplied together and 2 on the bottom. Now if we saw it like that, we might naturally realise that there are some cancellations possible. That is, 2 of the 6's on the top line cancel 2 on the bottom. What that leaves us with is the remaining 3 6's on the top line, or 6 to the power 3. And that's a good way to remind yourself that the shortcut to get from the beginning of that series of calculations to the end is simply to take the difference in the powers. And that formula you see above is a shortcut that goes through that process for you. Let's see what happens if we change the problem to a situation where the powers are both the same. So here I've got 6 to the power 2 over itself. Now it's not all that difficult to see that this fraction clearly must be 1, either through cancellation or simply by recognising that when you take a number and divide it by itself you must get 1. Now the beauty of the index law above is that it also applies in this situation. So here I'm taking 6 to the power of 2 minus 2, which is of course 6 to the power 0, and here we see a practical example of what a number raised to the power of 0 will produce. Because of the consistency of all the mathematical rules we're using, 6 to the 0 has to equal 1. So the correct interpretation of a 0 power is to replace it with 1. And if you have trouble remembering that, you can always go back to simpler rules of mathematics and derive the logically consistent result. The third item in our first part of the baker's dozen is what happens when you divide by 0. Most people have an idea that something interesting happens when you attempt to divide by 0, but are not terribly clear about what exactly the implications are. Now, you've probably seen stated that division by 0 is a process that is not defined, which is a tricky concept in some ways. Most mathematical operations produce something, some kind of number or formula or expression. Not to be confused, of course, with taking 0 and dividing it by other numbers. So 0 divided by 3, which is equivalent to the fraction 0 over 3, is a perfectly respectable number. 0 is a number, it sits on the number line, it's a defined quantity. The trouble starts in this situation when you attempt to divide any other number by 0. And the most you can say about those two statements is a word, undefined. It's a rare occasion where a mathematical operation doesn't produce a mathematical answer. Now most of us are aware of those restrictions. We're not always aware of why it's necessary to declare that division by 0 is undefined, simply not allowed. And a very good example that convinced me was an algebraic proof. So here we have a simple statement, variable A equals variable B, and I'm now going to manipulate that equation using some operations. So firstly, I'm going to multiply both sides by A. So now I have that A squared equals A times B. I'll also subtract B squared from both sides, which produces the equation you see here. Now both sides of this equation can be factorised. On the right hand side I have a common factor of B, and on the left hand side I've got the difference of two squares. So factorising both of those produces these expressions here. Taken the common factor of B out of the right hand side, and also use the standard method for factorising a difference of two squares. Now you'll notice that A minus B is a common factor of the left and the right hand side, so I'll divide both sides by A minus B to make the expression on both sides simpler. Now at the top we stated that A and B were the same, so I'm going to replace A with B, and I'll simplify a little bit, so 2B equals B. Then I'll divide by B, and I've just shown that 2 is equal to 1. And that's bad news. Mathematically, one of the bedrock principles of all mathematics is that different numbers are different. 2 does not equal 1. And we've performed a series of algebraic steps that appear to have proved just that. So the fabric of mathematics is in jeopardy until we work out what's gone wrong. And in fact, one of the steps I took in that proof was illegal, incorrect. Have a bit of a think for a moment about which step may be the culprit. Well, the offending step in this process is that one, the division by A minus B. You've probably done division by expressions like that several times already in your mathematical career. Why is this one wrong? Well, the answer is because we've deliberately stated that A and B are the same. Therefore, dividing by A minus B is inevitably dividing by 0. Since that step is not defined, then none of the following steps are allowed. The process is incorrect from that point onwards. So you get the idea now that division by 0 has to be not only declared to be illegal, it must never happen at all. And here's a visual representation of what that means in case you're having trouble with the algebra. You allow division by 0 to exist, you let that slip past you, then a kraken will rise from the ocean and drag your ship of mathematics to the bottom of the ocean. Now that was a fairly contrived example that we just saw. Here's a more practical problem where division by 0 may turn out to give us a hard time. We asked to solve this equation for x. X times 2 minus x equals x squared. What is the solution or solutions, if any, to that problem? Well, a good way to tackle a problem like this is to recognise that there's a common factor of x in the left and the right hand side. So we may as well divide both sides by x to make our job easier. So now we have that 2 minus x equals x. Rearranging that, putting the x's together, eventually produces the answer x equals 1. So we might be inclined to claim that the solution to this problem is that x equals 1. And that certainly is a perfectly satisfactory solution to the problem. Substituting x equals 1 into that equation at the top will give you a left and right hand side that are both the same. But there is a problem with this process. We divided both sides of the equation by a variable, x. And remember, a variable x can take any value at all along a number line, which includes 0. So what you should get into the habit of doing when you're working on a problem like this and you do divide by a variable or an expression involving variables is make sure that you specify that that expression or variable can't equal 0. So in this case, that division of both sides by x is only valid if we restrict x to values other than 0. What that means is that so far in our solution to the problem, we have considered possible values of x from -infinity to infinity, but excluding 0, which means we haven't tested whether 0 itself satisfies the equation. So we better do that as well. So we go back to the original expression you see at the top of the screen, and we substitute x equals 0 into it. Since it's a single value, we don't need to do anything particularly sophisticated other than work out what the left and right hand side are. So quite clearly, if you put x equals 0 into the left hand side, you get 0. If you do the same thing to the right hand side of that expression, that is, take 0 squared, clearly you also get 0. What this means is that x equals 0 is also a solution to this problem, one that was invisible to us until we checked the value of 0 separately. And the reason we had to check 0 separately was because the algebra we performed earlier was only valid if x did not equal 0. So the correct answer to this problem is that x equals 1 or 0 are solutions to this problem.
If you'd like to find out more about our services, including our workshops and drop-in sessions and study survival guides, visit www.studysmarter.uwa.edu.au or find us on Facebook and Twitter.